Sounds like it's So yeah, it's like it's, you know, like I pay such a broad classification, so it's so yeah, so for the that run those applications that have they are included. Like they're talking about chips, about technology that doesn't even exist on chips yet. It's tricky to say how that will work out. Okay. Where's the mic? So, this.
Thank you. This. Can you hear me? Well, actually, do I need to stand over there? Probably, right?
Yeah.
There's no box. That's why I'm confused. You know, I could as well do it from my room. Does it work? Okay, cool. Everything works. I think we should get started. Otherwise, we run out of time. We have only 1 hour, and we want to cover 2 topics. I do this together with Ming. I do the first part, which is more focused on the trusted execution environment and the trust zone technology, and Ming then explains to you why this is relevant for some standards effort that we have been trying to initiate around this Teep effort. And specifically, there's a protocol proposal that we put forward, which is called Open Trust Protocol. And so I hope when you walk out of the room at the end of this hour, you would at least have an idea on what some of the hardware mechanisms are about, and get an understanding of why we have been entertaining the idea to standardize this protocol. What's the problem there? Okay. But I want to start a little bit slower, specifically since what most of us have been typically working on in the IETF has been communication security protocols. So we want to deal with problems that, it's interesting that those two get out of sync. We want to deal with confidentiality protection. We care about integrity. We care about authentication. And there are some classical components that are needed for that. You obviously need to have the cryptographic algorithms that we either borrow from some other organizations like NIST, or we have some standards efforts in the IETF. We need obviously the protocols, and you will see a lot of this during the week with DLS 1.3, and a couple of other components like a random number generator needs to be present because most of the security protocols rely on random numbers. Key management and identity management, that's sort of like a core part of what IETF has been standardizing. If you look at RC 3552, which is this RC talking about how to write security consideration sections, that's what it talks mostly about, because that's sort of the bread and butter of this organization. But it doesn't stop there, unfortunately. So you also have to care about the system and software security. And so the problems that you typically will run into there are malicious software, whether this is something that someone installs, replaces the operating system, the whole firmware and you may not like that, or if someone actually installs from remote some malware. Many of the attacks, specifically on the server side, also care about unauthorized access, sort of database access to some protected resources. And so you have a few other components that are needed on top of what I had explained earlier, such as you need to have some isolation mechanism, and that sort of goes back into the really early days of operating system design, when you didn't want, like with MS-DOS, you had everything in a single address space, so you get one piece of software compromised. It basically allowed access to everything else. Needless to say that over the time, people didn't want that, so they had memory management techniques. So every application has the illusion of having full access to the address space, which in reality it doesn't. And things like protected storage, trusted boot, recovery functionality, and so on. So a couple of hardware mechanisms that have been, and of course corresponding software that have been added to provide this type of isolation. It still goes further because you also have certain classes of attacks that deal with the physical system. So if you have specifically in the IoT sector, that's a big concern. If you have access to the devices, then you have additional capabilities, and so you have sort of examples like power analysis or analysis. So you measure the power consumption as the device is computing cryptographic operations, and so in the worst case, you can see from the power trace on, and specifically public key crypto is very power hungry. So you see what is actually being done, and so you can actually, in the worst case, you can actually see, and I have examples on my laptop if you care about that topic. You can actually see what key is used. You can basically read the key from the screen. This is a static power analysis technique. Sometimes it's a little bit more nuanced, so you need the differential power analysis, which uses statistical techniques. Maybe some of you have actually been working on this already. So those sound like very sophisticated techniques, but they get more widely used as the tools and the hardware to mount these attacks get more common. But they may also be things like literally looking at the chip, looking at tapping on the buses to see the communication that's going on. So, and there are obviously countermeasures. So one is using algorithms that run in more constant time, encrypting memory interfaces, putting everything on a single chip, so it's more difficult to snoop on the buses, and so on and so on. So you have these three sort of categories, and if you look at what the industry has been doing, it came up with various principles to deal with these type of sort of security issues. And one is obviously, and a big specifically this one is this isolation principle, and then the least privilege. And I'm sure you've heard that before. So the idea here is, and that's sort of as somewhat of an assumption in this whole work, is that you have, so if this is, let's pick an example because the circles are probably not very illustrative, but if you think about a DLS implementation. In a DLS implementation, you have many components. You have crypto components that have access to the keys, let's say an AES algorithm, but you have many other components that actually don't need to have access to keys. For example, the whole processing of the incoming packets. So you get something from a TCP stack, you need to process those. There's, this, of course, a state machine as well. That may have a different security, or doesn't need to have access to the same keys. So you may want to separate those two things. And this is what this means. And of course, you can extend this to an entire a system, like the mobile phones that or the tablets that Dero is using. So you have an operating system like Android. You have lots of security relevant code there as well, like all the cryptographic algorithms, but all the apps that don't necessarily need access to the keys, of course, directly. So So that's the idea. The isolation is sort of separate the parts that are in some sense non-trusted from the ones that are trusted. And the trust term is, I'm not a big fan of this trust terminology, but I'm using it nevertheless because that's what the industry has been using. So trust here means it's a little bit in the eye of the beholder, of the developer, what you consider trusted and where you put the demarcation line between what you consider trusted and what not. So you as a developer, so if you develop a system, put something together, you decide what you consider trusted, what you put on the untrusted side versus the trusted side. Trusted by you to do whatever that specific application or whatever the piece of software and hardware is supposed to do. So not necessarily to be religious. There's no tag of trusted stack or something, trusted software in by itself. It's just the question of how much review did that software got. Do you have any confidence in the security quality of it? Okay. And ultimately, you want to reduce the attack surface on those components. That's the idea why you introduce this separation. And so here are some examples on what people typically consider sort of trusted software that requires more protection. So typically, what you want is to keep that part as small as possible, and you want to do a lot of review, a lot of testing. Maybe you do certification, and sort of like you want to spend a lot of time on this. So of course the effort then goes, or even for some security software, you may want to do formal analysis of the code and so on. So it can get really, really expensive and time consuming. For the other part, it's clear that you can't do this for all of it because your progress will stall pretty much. If you look at an ordinary full-blown, what we call here, rich OS, like Linux and so on, it will take forever. And for some of the components, you may actually, as a developer, you may not even have the components in a source code. You may actually have to deal with libraries, so you would probably consider them untrusted because you know very little about them. Okay. And so, so if you plot this on a sort of like this diagram, you have different attacks that you worry about, and depending on what you actually are trying to accomplish, you care more about hardware attacks, the ones that I mentioned, where you actually someone takes the chip apart, or if it's more side channel attacks that I mentioned earlier, these are non-invasive attacks where you just snoop on the power communication, or you have you have software attacks where you have buffer overflows and return-oriented programming attacks and so on. So what you want to avoid is, so if you deal with, for example, if you want to, in your product, if you want to deal with those two attacks, software and the non-invasive hardware attacks, which is quite common for IoT devices, you want to avoid the case that someone mounts an invasive hardware attack once and then can actually do a scalable software attack, because that would be obviously very unfortunate. We see that in IoT happening quite often. So if you build class keys in your IoT devices, same key in all devices or in a large number of devices, someone will go ahead and spend the effort to find out what that key is using invasive techniques, and then he can go and mount a very simple software attack because obviously he knows the key. He can then, for example, compromise the firmware update mechanism. Those are, for example, you look at all of them and make your risk assessment and figure out what you actually want to do. And I will explain a little bit later what we see this diagram again to explain you what some of the technology does and what it doesn't do. Okay, getting into solutions. And one of this isolation technique is a trusted execution environment. And what it and as I said, like these operating systems are fairly large, so you want to have some isolation with those. And the idea of having these trusted execution environments is actually fairly old already. Like we're talking about 15 years potentially, so they are not. It's not something that was developed recently, but it takes some time in the market for companies and consumers to actually pick those up. You, for example, nowadays have them all in your devices and mobile phones and tablets and so on, but they are only used to a certain extent because developers have a hard time to use them. So the idea is you take a tablet and move some of the functionality out of the Linux distribution and move it into this trusted execution environment. Pretty much what I have been saying previously. But there needs to be some components there. So the trusted execution environment is just ultimately hardware, but you need to have software as well. And unfortunately, there are some differences in the way how different companies develop that technology. So I can obviously best speak for ARM, my employer, because I'm more familiar with the technology we develop. There will also be, or there was a tutorial, not a tutorial, a presentation at the BOF in the Chicago IETF meeting given by some Intel guys. And they are going through a full-blown tutorial about their technology after the IETF meeting. It didn't work out beforehand, so you're encouraged to also have a look at that, because it's just a different implementation of how they do the trusted execution environment, to see what the differences are. One of the differences is we use in our trusted execution environment, we use a sort of a trusted boot process, which some of the Intel technology, for example, doesn't do. Like the SGX doesn't require that. We also we need an operating system there, small operating system that handles the applications. But I will get to these diagrams a little later. So you need that. So inside this trusted execution environment, you have the code running, which for these different purposes, whatever you do. For example, Ming is going to talk about some use cases, and I have a FIDO example. So if you have a FIDO application running, and let's say a banking application, the FIDO application is not supposed to look into data and code what the banking application does, quite understandably. There's only one trusted execution environment per chip in this model, and so you need to separate these applications again. So isolation within isolation in some sense, like an ordinary operating system also isolates among applications, among processes. Okay. Oh, yeah. The other sort of crypto services are fairly obvious. Sort of cryptographic algorithm storage, random number generation is also needed, because otherwise, how do you do the crypto? So here's the figure again. So the trust zone-based DE is specifically designed to deal with these type of attacks. If you want to also have protection against invasive hardware attacks, then you need to have something like a hardware security module or secure elements that are specifically hardened against those. So that's just as a differentiation on what these things provide and what they don't provide. I will go a little bit into how ARM's trust zone technology works as an example of a trusted execution environment. To have at least one example, so we don't just talk in the abstract. In the ARM architecture, there are different types of so-called profiles, and I specifically in this talk about this profile. That's why I put a blue box around it. It's the A stands for the application profile. That's the type of processor you find in the tablets and the mobile phones. And that's also the version that has the trust zone support. There are other profiles, like the real-time profile or the microcontroller profile, which they also have trust zone capabilities, but they are a little different. Different in terms of how far they are along with their maturity. So for example, the microcontroller profile that's used typically for low-end IoT devices, the chips are not available. So the trust zone capability there is not available in chips. I can show it to you on a simulator, but not on a chip. So it's think about it as like while some of the stuff is deployed and you have it in your hand, versus some of the things that are on paper and companies are working on it, but not available. You can't go to the shop and buy it, versus complete research projects, which are technologies I don't even talk about, but there are other efforts ongoing where things are more speculative. It may happen or may not happen. Who knows? That may be interesting for the IETF, but not necessarily for the standardization efforts now. This A-class, as you can imagine, is a 32-bit and 64-bit architecture, has different instruction sets. And if you remember the days when you did in a computer science class on computer architectures, you had on one hand the instruction set architecture, and probably you looked at the Intel instruction set architecture, and ARM instruction set is just a little different because it's a RISC instruction set, reduced instruction set, versus a CISC, which is a more powerful instruction set. So that's one of the big differences. But I will explain a little bit more about some other differences. Graphically, what it does on this trust zone for this A-class architecture is, as I mentioned, there's essentially 2 operating systems running on a single chip. First of all, this is the operating system you obviously see as a user when you turn on your phone, like Android. But then there's also another operating system running. It's not running concurrently, but it's not a multi-core processor. It could be a multi-core processor, but it's still the trust zone support is sort of, and that's what the error is indicating. It's like you have a function call that happens here, and then it switches over there, that executes, for example, the security functionality, and then switches back. It's not running concurrently and sort of monitors what the other operating system is doing. That's not what it does. And these secure apps, these trusted apps, then sit on the secure OS. And the way it's designed, it allows developers like you to write your own operating system, or to get one, an open source one, or to buy one. So there are many different operating systems of running for this secure side, as there are many more as actually for the normal world. And so these applications then need to get somewhere there to that part. And the secure monitor makes sure that this transition happens securely. So it basically, every time this operating system says, I need some security functions, it needs to go through the secure monitor and figure out whether that's actually permissible for obvious reasons. So there needs to be a clear entry point into the functions, because otherwise you could just jump randomly somewhere into the code. Just for illustration purposes, and I'm not going to talk about more about it, this upcoming trust zone for this embedded architecture works differently because IoT devices are fairly small, so they are not going to run 2 operating systems. They are barely running one, so there are some optimizations taking place here, just to see the difference. When I talked about the instruction set architecture, one part of this sort of programmer's model, a programmer's view, is besides the actual instructions that you can invoke on a processor, there is another important part, which is actually how the memory model works. And in the ARM architecture, everything, all the peripherals and the different memories actually all mapped into the full memory space. So depending on whether you have 32-bit or 64-bit, everything is mapped into the memory space. It looks like you're accessing memory, but in reality, you're actually accessing different type of peripherals. So for example, I2C is a communication mechanism to typically access external peripherals like a fingerprint reader, a display, and so on. And what Trust Zone then does is it basically replicates this available memory region. It adds another bit and thereby doubles the address space. And so you can decide which part or which peripheral you want to make only accessible to the secure world, to the TE, or which part is accessible to the normal operating system. So the separation happens via the address. And even to extend that even more, it's not just the memory. Here's an example of a system on chip, which just means that normally you put a lot of different components into one chip. It doesn't mean much more. And some of the components, for example, in a typical system are actually off-chip. So for an A-class processor, you typically have the memory off-chip. It's a DDR RAM. So if you look at like many of these devices, you just have a bus to the memory. So obviously, from a security point of view, that's quite important. It makes a difference whether you snoop on a bus or whether that bus is in a chip, and you first have to basically open up the chip to actually see something. On an IoT device, for example, the RAM and the flash would actually typically be on a single chip. So everything is back together. But what then TrustZone does is it extends this protection across the whole system, or the whole system on chip. So that's why, unlike a smart card, for example, a secure element, it doesn't just protect the algorithms and the secrets that reside on that chip, but it actually extends to the whole system if you want. Of course, you cannot use it. So here specifically, because it fits the example I want to show in a minute, for example, there's a fingerprint reader, which is only accessible to onto the secure side. So what you can do is, and I'll go jump to this FIDO example. Actually, I jump to it right now. To this FIDO example. Who knows FIDO? Have you heard about FIDO? Because otherwise the example is a little bit tricky. You know, a few know FIDO. FIDO is an organization, an industry alliance that tries to define, standardize an authentication protocol to get rid of passwords on the internet. Okay, a fairly novel cause, but quite difficult to do. And the way they do it is they use public key cryptography, and so they create, they define something what's called authenticator that creates a public-private key pair, and when the device or a website like here, when a website asks for authentication, it basically trickles through a plugin. It trickles into the OS, because the crypto functions and all the keys then in this, this is a possible implementation, then reside on a secure world, because you don't want to make the keys accessible to like an Android operating system. You don't want to store it on a file system or something like this. So you have this authenticator there, and on top of that, you also want to prevent malware from just triggering an authentication attempt, so you actually don't know what's going on as a user. But every time you do the authentication, you are asked to, for example, in this case, there are lots of different ways to do it, to use your fingerprint to release the access to the key. And so, obviously, a crucial aspect is to also protect the fingerprint sensor and access to it, because if the malware could just get access to that, then what's the point? They could just fake everything to the user, and you wouldn't know what's going on. So the fingerprint reader is also only accessible in the secure world. And that's what you see with some of the FIDO implementations on smartphones. Could be a fingerprint. It could be, I've seen cases where they use face recognition and all sorts of stuff. And you also want to, for privacy reasons, you want to store the fingerprint template also in a secure place. You don't want to make that accessible to like apps, for example. So this is one example. So obviously, if you now add FIDO to your phone, the question is, how the heck do you get this application there? The FIDO authentication piece, not the piece that interacts with the web browser that passes the messages and so on, because this is JavaScript and so on. Okay, and I'm actually getting to an end, and hand over to Ming. But before that, people always like open source, play around with some code. There is actually code if you if you want to test some of those systems, like work on it yourself, play around with it, see what it does. Sort of the hardcore version is you go and get a reference implementation of this. There's a project called Opti, which implements, and this is the figure taken from there, it implements the Secure World OS, and it implements some of the components that are needed on the rich OS as well. So you get those, and you can extend it if you want, or do something else. There's also for the firmware, which is sort of like the lower part that interfaces with the hardware. You can also get that as an open source. But there's obviously one important part missing. You need to have the hardware. You know, like you can't just run it on random things. You need to have a hardware that allows you to do whatever you like. And here are two examples that I think quite inexpensive. One is the Raspberry Pi 3, a new version of Raspberry Pi has trust zone support, and there's a company that did a reverse engineering of it. So the guys who worked on the Raspberry Pi, they weren't really eager to release documentation on what they had been doing. So this other company just reverse engineered it. And there's code available, so you can actually then, they did a port of the Opti to the Raspberry Pi, so you can load it there and watch the video and get some applications running, or write your own applications. That's sort of probably the cheapest entry point. A little bit more sophisticated, but not much more expensive is there's there was a Kickstarter project called USB Armory, which it looks like this. It's a USB stick size device with a ARM processor on top of it, with some RAM. And they also have trust zone support because they specifically focused on the security applications, and they are applications that you can download from a Bitcoin wallet to whatever. So you can develop your own banking app security mechanism or so, or a FIDO client if you want, and run it there. And with that, I hand it over to you, Ming. So I hope this sort of isolation concept made some sense as a way to reduce the attack surface on the overall software, and the DE is one possibility to do that. And I walked you through some of the trust zone features, and I'm happy to provide you more information. There's obviously a lot of details to look at if you want, depending on who you are as a consumer of the technology, if you want to develop a chip versus writing an operating system versus all sorts of things. And I posted some of the documents and pointers to the mailing list, to the Teep mailing list, if you want to dig much deeper, also videos. Okay. Ming. And if you have some questions, oh. So my understanding is it was written from scratch, but it's for these A-class processors. It's not an IoT OS. It's yeah, it was new, designed by a couple of different companies. ARM is contributing to that project as well. Yeah. Yep.
Can you make a press execution run about this?
Good question. So it depends on your definition on exactly what the trusted execution environment is. So, for example, with the presentation we had at the Chicago IETF meeting, the Intel folks considered a TPM as a trusted execution environment, but there are certain maybe limitations, if you will. So there are obviously differences as well. So that it doesn't aim to TPM doesn't aim to extend through the whole system. So you will maybe lose that part. There's also the question of which version of TPM are you actually using, and if you want specifically this feature, which we are going to talk about, where you actually have different vendors providing different OSs, and whether you then have a possibility to update the software, which is something that I think TPM was not really designed to do. So if only you can update software on whatever hardware security module you have, then the interoperability challenge to work with a standardized protocol gets a little shaky very quickly. And so I think at this point, I think Trust Zone is an example where some of those problems arise, and they don't arise for, let's say, some other software or for some other technologies. And since TPM has been around and there has been maybe not so much interest to develop such a protocol, maybe that's an indication of a more closed ecosystem.
Of course, the Teep is primarily designed for secure and verifiable code. By itself, you can't protect the running code. That's what people are having.
Yeah. Thanks.
Are you? Yeah. What I talk to continue with this, all this contact. Now you have security environment. What's the problem do we have? So what's the problem? Why we bring to the IETF? So what's the problem we want to put into some more interoperable standard? So that's what I talk about. So what's the problem we have? So with that security environment, we want to have the applications. Sorry. So we want to have a trust application. Why trust application? Where do you need trust applications? There's multiple set here. This mainly like startup case is more like for Android operating system for mobile. Like start for simple for mobile, right? Mobile is a mobile phone so much, like market is so big today. You have Android app, we tend to not trust that much, right? It's for the Android environment. So now you have Trust Zone and mobile chip. You have TE there. You can run trust applications. So what are trust applications? You use a bank app today, like a payment app or facility PayPal and so on. But those I consider that not it's one for use case. But many bank apps I use Cheers, Bank of America, many mobile apps. When you have a more sensitive operations, where do you run? How do you protect that authentication key? How do you protect the authentication? And we actually, by the way, I'm from Semantic, right? I'm not promoting anything here. Just give you an example. We have a security application, a one-time password application. You can say Google Authenticator, right? Many people use Google Authenticator, right? Google Authenticator, where's the key stored today? In a sandbox in Android. You can steal it, copy it, clone it, very easy. Yeah. So what we did is we put into actually trust application. We have app in normal world Android. We run a trust application inside TE today. We have that. It's in market today already. Then there's one for the app. So when you have security operations in Android, where do you run? Typical use case, you run TE. Okay, we have TE here today. Actually, that's a problem, right? You have multiple TEs here. You have multiple applications. And you have game applications. If you have a game credit, game transaction, so on, certain secrets, where do you run? You can run normal world, or you run mini, tight, simple trust application running TE that give you protection, right? Banking application, security operations, enterprise, well, the enterprise they may have applications. Banking app is one for that, right? So with that, okay, you say, you run Google Play, and you download app today. Why is this a problem? You just install it. I say that's a problem. When you need some standard, when you have multiple players in the market, right? You have multiple TEs. Okay, I think that's my next slide. What's the gaps, right? What's the gaps? One of the gaps today, how do you remotely install your application? You have normal app today is download, just install. That's where the problem happens today. Using install many malware apps, right? So you know what Google does is do a malware scan, right, periodically, but it's not a catch in the beginning, right? Now you have a secure OS, you have TEE, you have Trust Zone or other technology, you have the secure chip. On top of that, your application need to be more matching that, right? Really make sure it's secure. You don't want just to download and run. Anyone can download and install. You need somewhere to manage it. But that's missing, right? There's no standard management protocol today. You can run an app through proper protocol. That's what we did. through proper protocol, proper vendor will lock in and say, install into certain TE environment. That's a problem. Okay, that's a problem. Now we have the IoT. I would say IoT more like a set-top box, smart TV, those ones. Anywhere you allow third-party provider applications. We're not talking about the ecosystem where you have manufacturers, you pre-install apps. That's another. There's no problem there. Right? Manufacture pre-install anything you want, right? It's sealed down. Like there's a thermostat. You put an app there. There's no security problem, right? Whatever they have is they can control it. Anyway, it's not our plan, right? But if you have a platform, allow many application develop, or many vendors develop, now you create a problem, right? Create a problem that come in here. Say you have multiple TEs. I know at least 6 TEs today. Okay, 6 TEs today. 6 OS. You have multiple service providers, banks, game players like us, security providers. You have many applications need to install there. So how do you push in application to multiple different TEs? This is interoperability issue, right? Interoperability issue. So that's the gap. Many application vendors, now you have device manufacturers, OEM vendors. They get chips, they get TUS from some vendor. They crumble into a device, right? Whether it's a smart TV or it's a phone, whatever, right? You have many of those vendors. They have chip vendors who provide chips. This is what I talk about the MOM example as architecture. Chip vendors and many, right? Also many of the chip vendors. Many of them. Go ahead. Did I lose you?
Point that I forgot to mention, like ARM just develops a blueprint of the architecture. It actually doesn't produce the chips. So that's why you suddenly have these different chip manufacturers and hardware vendors. Maybe that's so it's a little different from some others like Intel, AMD, who develop the design and then produce their own chips. So you suddenly have a more diverse ecosystem. That's why we can't also not mandate what operating system that people run. So that's why you have lots of different operating systems.
Right. So then with the problem big enough, I would say, this one's mobile, let's say even mobile IoT market set, right? Mobile and IoT is big enough market, right? And how many devices we have? I know along ARM chips collectively by many vendors, you get the number. How many chips today each year? Yeah, 10 billion, 15 billion. The later, 15 billion each year, mobile chips shipped. They have trusted environment. So if you have trusted app, you can leverage that 15 billion secure environment for your app. You don't have to run Android, just that security. You don't have to suffer from that. But now that you have an app, you do want that. We write the app, problem is that can run more apps. Running there, quickly install and manage. That's the problem we try to address. Okay, I just want to spend a few minutes on problem statement. Whether that's something you see the problem, we need to have interoperable protocol here, right? It's really facilitate many service providers, many application developers into this open environment. I can consider this open environment. Well, anywhere you have open environment, multiple players, you need interoperability. That's where we come in. Okay, for that we solve the real issue, and then they say what propose a protocol. For that, we propose called Open Trust Protocol, or name-wise. But what it does is we propose an interoperable protocol which remotely manage the trusted application. You can install it, update it, and terminate it. Yeah. To that end, what provide is a support multiple TEs, multiple server providers, multiple chip vendors, open environment, and any company can play as that TAM, or trusted application manager. Right? It's open market. Right? That's what is coming. Yeah? And the two properties we want to achieve: mutual trust, or what do you mean trust? Hand is done like broad. What do you mean trust? Let's say it away. And many of you have mentioned TPM. Two properties. First one, remote attestation. I want a server provider. I'm an application developer. I want to know which phones allow my application to run. I know that's a really trusted environment. I did trust, right? I install my application in some TE. What is that TE is buggy, not secure, right? I want to know what kind of devices I can verify, so I install my app, manage. So remote attestation, say remotely I know that device, that one way. Okay, server provider remote attestation, the device. Otherwise, the device need to know which provider is delivering me the application. So I can define policy. I just trust the application from this set of vendors. It's a user choice or enterprise choice. That's open. This product doesn't matter, right? But you give that policy choice, they can choose which kind of application they can install, right? So that's a space it fills in. Okay, space fill in. For that, remote attestation, mutual authentication will leverage a certificate. Okay, certificate scheme we use here. Okay, scheme. There's another way to do it. It's open for discussion. As long as we say this is primary address, what's the security scheme we put in there to enable that mutual authentication? That's open, right? For now, we pick certificate. Because certificate, many of you in this room, right? You know it's have a very good scalability and to resolve that verification, trust verification. Yeah. So this space, the OTRP solves two problems. From trust application manager to the TE side, how the application can be remotely mutually verified. TM can verify this TE running here is trustworthy. And this side can verify TM is trustworthy. The mutual side trustworthy, then allow you to proceed to install and manage your trust applications. Yeah. And to that end, there's two more players in this. This is not an inline protocol, it's offline. It's you get a device certificate, a device key inside your device in TE side that enable you to remotely verify by server providers. Okay, a certificate used here. Okay, this TA CA, you can host your own CA, but you need to get your server trusted by your service providers. Okay, it's their choice, And again, device need to verify server provider remotely. Server provider at today, like a website, similar. You verify organization, right? You buy certificate. That's forcing a standard practice, like a standard practice. We leverage standard practice, but fill a gap here to remotely manage applications in open environment. Yep.
I have a question. How you define the attestation field? I think it's different from our previous understanding working with attestation. Here you just use some certificate to do the mutual authentication.
Right.
To verify their mutual identity.
Right. Right.
But remote attestation also includes other parties that you need to verify your peers integrated. Software integrated, it's hardware integrated. That's a concept in TCT or in TPM framework. So
that's through delegation here, right? So you remotely verify this from a device certificate through a TE verification. So remotely verify this identity, as you said, but it's a device identity. Then it's not device identity. It's will verify which TE vendor you're running. Do I trust that TE? And under below there, you will see later, there's even firmware. It's a firmware and TE, both the information are part of verification data.
Currently, there's one proposal for attestation in the document, and on a mailing list, other people have proposed other, like Intel had proposed their EPID scheme as one possible with different properties. And it's obviously would be something in a group to discuss what is the right attestation mechanism.
so it's not yet decided what we really want to achieve by the attestation. Maybe a simple attestation, maybe more complicated.
Yeah, we have one here is through delegation. So all the way we can trace verify the device have secure boot and secure firmware and secure TE. That's what service provider will get through that step. It's not an identity. It's a secure boot, secure firmware, and secure TE. That's three verified by service provider. No.
It's basically trust the key
Right.
Because everything is stored in firmware.
Yeah, firmware have key pair actually. It doesn't. Yeah, it may have a certificate, but that one's relatively it's not a store requirement. Yep. So that gives you so what as a design choice today we use asymmetric key in the device, not symmetric key. Asymmetric key and we promote the use of certificate. Other technology may be possible. We notice different variations for remote verification, like a FIDO, right? We choose different 3 ways to do that. Okay. Here we use a certificate as a primary choice. From message-wise, this is a message protocol. Again, it's a message protocol. We mentioned it. We leave that network layer to the implementation. So it's a message protocol defined trust, mutual authentication. Okay. We choose JSON message. Okay, JSON message. The reason we choose JSON is you can leverage the JSON signing and the encryption already defined by RFC. So that's already standard we can leverage. We don't need a invented VL. So we need a little bit small agent in a normal world to relay this message. In order to talk with TE, you need something to talk with TE, right? You need something. We don't want every developer to write that. So that will come say this is needed piece. Go ahead.
Check if that ERP agent is not trusted and particular, not relying on to preserve integrity communications.
Right, right. So we see more. Let's see, right? Today, that's OTRP agent, pure relay agent. It's a black box. It cannot open the message itself. It's end-to-end. Okay, got it. That's okay. So far we say support device has only one TE. Someone asked if I run 2 TE in one device, possible? Not really common in market today.
But if it's a black box and you don't open the message, so how? What is the use objective?
So you have, like I said, you talk about this diagram. Okay, I will go to this one here. What's needed here? Okay, come in here. TE and TM mutually, every message entering security encrypted. Message encrypted. So, but when it comes to here, in the rich app will talk with TM from Android. Let's say, I just simplify, it doesn't have to be Android. I just take example. You talk with TM, you get a message back. You need to send this message to TE. How do you send a message to TE? You need some application to do that. OTRP's job, this agent job, nothing more than just relay that message, whatever you get, binary data to TE. So we expect TE vendor to provide this agent. They know how to talk to TE.
It refers to what I briefly mentioned, that the secure world OS doesn't just run in the background and waits for messages. It's not a sort of like God thing in a book that waits just for messages, but instead it needs to be invoked from the normal world OS. And that's what you need to have, something that makes this call. This is the agent that makes this call.
So without this, that means you as a application developer, you run just this regular application. You need to run how to talk with TE. That's a burden, right? But if this is given, what you call is just simply standard API. What we want here is to define API, not define software. Just to make that clear, right? No. Yeah. So this one just more like interface. Okay. So for that, and then scope is that what is like this protocol, what you try to scope the two parts. One is what kind of message will be exchanged between TE and TM. It's JSON message. We define only the JSON message format, what the content should be, how it should be signed, how it should be encrypted to ensure end-to-end security. So that part. We don't. There's other players in the ecosystem. We just say you have a security key here. How to get it up to you? You get a good talk with some CA or your own CA, as long as your counterpart trusts you. Okay. How to define trust management outside of this? But we define message protocol exchange. That what once have a standard. Now you can talk with different TM managers, vendors, to distribute and manage your application. Like if you're a game provider or your enterprise apps, and you can work with the trusted application managers to manage that. So for that, 5 minutes. For that, I have this message defined totally. You can see here 6 messages. I can see messages. We call it 6 messages or 6 commands. First one is to get device state. So every time come in, first step, I will query what is currently running a device. Is that device trustworthy? Okay, query it. What's a TE? What's a firmware? It's a TE firmware, and what's the security domain application running there? So that I query whether I need to upgrade my application. Is TE trustworthy? Like get device state. Okay, remote call. Then if the clean device, you start with security domain. Okay, in this case, TE trust application running inside security domain. Okay, usually each application provider have their own security domain. Okay, that's how the partition today. You create security domain, update security domain, and delete security domain. And once you have your own security domain, within one security domain, you can install multiple trust applications. Those are further isolation, I would say. Hans mentioned isolation important. Inside TE, now use a security domain as a scheme of isolation. The core different security domains. The keys are definitely they cannot access each other. Applications between 2 security domains usually not communicate each other, but you could. It's depend TE choice. You can say, well, if you manage 2 domains, whether they can talk to each other, that's TE implementation. But you have security domain, and inside security domain, you install applications through API again. Install, update, and delete. That's 3 APIs, or I call it APIs, they're too developer oriented. So 3 messages, okay? 3 pairs of JSON messages. And then what the other element you need the keys? In the device side, you have a TE key pair and a certificate. That today, so you have a unique key pair and a certificate per device. Okay, you trust by CA. So TM will trust TE like this here. Root CA list of TE certificate. Okay, you trust TCA. Okay, trust CA. So that enable you have unique certificate. Firmware you will have key pair and optional certificate. When you boot it, that firmware signed and we pass to TE. And the TE that get device state will include piece of information about the firmware trustworthy. Information sent to TM. TM says, oh, okay, you started with firmware as signed, and then TE also signed. Now, this is set of TE and T firmware I trust. So TM says, now, so okay, this is comply with my policy. I'm going to install my application into those devices. If the devices are compromised or not trustworthy, not in the environment I trust, I do not distribute my applications. That's the purpose. TM side, this is really standard organization certificate identify which TM you are. That's a standard one. Service provider, again, service provider has organizational certificate, you sign your application. So that TM device side can make choice whether it trusts you, right? They can make a decision. So that's the main ones. Each side, service provider side and TE side. I recognize this one. This is a multiple one-to-one relationship. Sample workflow is like this. It calculates 1 minute. So start with the clean. You do the client application, normal app. You run I'm a regular developer. I run an app, talk with the TM. TM says, I want to install my first trust application. You talk with your trust application manager. Trust application manager now go to talk TE. So you want to install device. Is that device trustworthy? It'll ask that get device state. It comes back a bunch of information about the TE and the firmware. So TM says, okay, this device follow my policy. I allow you to proceed to install TA. So now it's a send a command, that message say, create a security domain. First time, this client app will call OTIP agent, send a message TE. TE will decrypt it and create a security domain. When it finish, send a status back. Now you further say install TA. You can send over trust application as data. Okay, application is really binary data, along with any personalization data. Right? You have application, you initialize it, you personalize, all data sent over, encrypt it. only that device can decrypt. We don't know what talking about detect here. Only device detect. Anyone in the middle is not able to open it. Yeah? So that's some flaw. In summary, it's a, okay, that's a problem statement. What we're trying to address, you have many TEs in a secure environment, open to many companies develop applications. You want a interoperable trust application management protocols. Okay, so this hopefully address interoperable issue and boost and promote the use of secure environment, have the more secure applications, have the more applications to run in trusted way. All right, that's it. That's it. Any questions? Yes.
When we interacted on this, I think I understand from the mechanics point, one agent is in communication path between
Here.
trusted app edge and trusted environment. Why is the client app also there?
Oh, client app say, who is going to initialize the trust application installation? Typically, say trust application alone does not run. Right? It's hidden. Your interface, your external visible ones, mostly your regular application. You have payment application. You have game, right? Game application in mobile device, or it's playing your smart TV. Right? That's your app. That's a regular app. But now, in order that, say my security sensitive operations, I want to run a trust app in TE environment. That's where I want to install it. That's a typical usage. That's where this is in the picture. For that client application is responsible to talk with TM. Say, I will start that procedure. Remaining parts now you have a networking piece. We do not define network piece, but network piece when message sent back, where is sent to? The phone, inside the phone, let's take example phone, simple one. Phone talk with TM, you need something there. Right, right, good, yeah, yeah. Good.
Before you leave on Wednesday, if you look at the Teep meetings, Theo and Nancy, who are the chairs of the Teep, have been chairs of the Teep board, and they need to separate have sort of organized the room, reserved the room so that we can have discussions about the charter and some more technical details in a non-tutorial type of style. And it's at
yeah, the room is don't ask me to spell it. It's TYROLK. It's in this floor. It's just around the corner. So as you come out, it'll be on the left-hand side. And it's Wednesday at 1:30, I think.
yeah, it's on the info is on the list.
Yes.
You know?
And we put a link to the wiki for the meeting. I think we really should put strong focus to the charter so that we can be ready for Singapore. So just come with your questions.
And we'll upload, I don't know where the slides, whether they have been uploaded already, have they?
Yes.
Oh, okay. Yeah, so that's good. Yeah. We also have the recordings of the meetings, of the webinars, and
Yeah, I know
one
we
more
have the
recording. We still have to figure out where to put them because they are a little larger in size. I don't know what the procedure
Yeah, I
is.
don't know what the procedure is for Tom. I'll ask Kathleen,
Yeah.
the secretary.
That probably takes a week.
I don't know if you can upload.
We don't have wiki, because when I put stuff on the wiki, they took it out. Because they said you're not a working group.
No.
But thank you guys for coming.
Thank you.
I did.